720,000 years of ice, can tell us about climate change in the past. An Antarctic ice core details changes in the Earth's temperature, rainfall, and wind over hundreds of thousands of years. In 2005, on an Antarctic ridge that's considered the coldest place in the world, a team of researchers plunged a drill through miles of ice. Once complete, the hole looked like a nightmarishly deep toilet, complete with a little blue lid that plonked down after the metal drill dropped out of sight. The mission, led by Japan's National Institute of Polar Research, was to extract nearly 800,000 years of Earth's climate history, left as an imprint in ice beneath the surface. The 2-mile-long ice tube they extracted isn't just a window into the past, it may also give scientists a glimpse of the future. The ice core contains detailed accounts about how the Earth's temperature, rainfall, and wind changed over hundreds of thousands of years, and can help scientists fine-tune their projections of climate changes to come. The latest finding from the ice core, according to a new study published this week in Science Advances, suggests a link between the climate in Antarctica, at the southernmost point of our planet, and the Arctic, located in the very north. Data suggests that when the Arctic would cool, the Antarctic would warm. The research team believes that the inverse relationship between the two poles is due to an ocean current that keeps Europe and North America warm during the winter. Called the Atlantic Meridional Overturning Circulation or AMOC, this current shuttles warm water from south to north, keeping temperatures in the North Atlantic from plummeting during the winter. It influences rainfall and wind patterns across the planet, and circulates nutrients in ocean. In other words, the AMOC is incredibly important for the planet's global climate patterns. The problem is, we don't know exactly how it could change in the future. Because of global warming and also because of the ice sheet melt from Greenland, the AMOC could change in the future. And it is very important to model this, says Ayako Ebauki, a climate scientist at the University of Tokyo and one of the lead authors of the study. But the best predictor of our future may be our past. In projecting climate change, we're going into unknown territory, says Tom Delworth, a geophysicist at Princeton University who wasn't involved in the study. The more we understand how the past works, because the past had very different climates, that gives us better confidence in projecting into the future. So Ebauki's colleagues, a team of researchers from the National Institute of Polar Research in Japan, drilled deep into an ice dome on the East Antarctic ice sheet called Dome Fuji. They extracted a core that spanned more than 700 millennia, including about 7 cycles of glaciers warming, melting, and warming again. The layers in the ice sheets are a lot like the rings in a tree stump. They can tell scientists about the environmental conditions when the layers formed. The presence of dust can indicate dry and windy periods, with gusts strong to blow debris in from South America. And the molecular compositions of the ice tells the scientists whether a layer formed during a warm or cold spell. By analyzing the ice core, they discovered that Antarctic warm periods corresponded with climate fluctuations detected in ice cores extracted in Greenland. These fluctuations started with a brief period of warmer temperatures, followed by a longer stretch of frigid temperatures. To figure out what was causing the global climate to seesaw from north to south, the scientists turned to climate simulations. They adjusted their models until they came up with a set of conditions that seemed to recapitulate the fluctuations frozen into that 2-mile-long ice tube. Based on their newly calibrated model, the scientists could tell that freshwater melting off the Greenland ice sheets slows the AMOC's churn. That increases precipitation across the southern hemisphere, decreases wind speed over the Southern Ocean, caused the south to warm, and the north to freeze in their simulations. This current seems to have been especially vulnerable to freshwater during Goldilocks periods in the middle of Ice Age cycles, when the Earth wasn't completely blanketed by ice, but also wasn't entirely thawed. The researchers suspect that's because during ice ages, the ammox churn is already suppressed by a layer of ice. And in the warm periods, a small amount of fresh water couldn't prompt enough freezing to make the climate seesaw. Understanding how the climate changed in the past can help scientists narrow their predictions about the future. Which is challenging, because no one knows how much more greenhouse gases people will continue to pump into the atmosphere. But Pepin Backer, a geoscientist at the University of Bremen in Germany, has calculated that if the Earth warms more than 4 to 5 degrees Celsius, the ammox could collapse, possibly even as soon as the year 2300. Modeling and paleoclimate data suggests it would change many things: position of the rain belt over the tropics, it impacts the monsoon systems, Backer says. So yeah, really, a full collapse, that has a major impact on the climate system, and also on the circulation of the ocean nutrients in the ocean. That would make the future of the climate very uncertain if we go in that direction.